I'm Seema and welcome to part 2 of the chapter Chemical Equilibrium. Before we come to chemical equilibrium, let us now study about equilibrium in physical processes. And the physical processes which are most commonly observed by us are phase transformation processes, that is, the changes in the physical states of substances. So let us start our study with phase transformation processes and understand equilibrium in these processes. The phase transformations or the change in state, we have three physical states. We did that in states of matter: the solid state, the liquid state and the gaseous state. When a phase changes from one state to the other, we call it a phase transformation. That is, a solid, when it turns into a liquid, we call it melting. When a liquid turns into a gas, that is vapor, we call it boiling. And the third is where you have a solid turning directly into a gas, which is known as sublimation. So we're going to study these three transformations first and understand the equilibrium, that is, the two opposing processes in these phase transformations. So the first one is where you have a solid-liquid equilibrium. What example do we take? Let's take a thermos flask. And in a thermos flask, let us add some ice and let's add some water. Now, the temperature of this thermos flask is 0 degrees Celsius or 273 Kelvin. And when you opened the thermos flask, the atmosphere was present in it. Therefore, the pressure inside was 1 atmospheric pressure. When you added the ice and water, the pressure remained constant because till then, you only were adding the solid and the liquid, and the pressure, the gaseous pressure, was that of the atmosphere. Now you just tightly close the lid of the thermos flask. And what do you observe? You observe that the ice and the water, they establish an equilibrium with each other. And when I say they establish an equilibrium with each other, what do I mean by it? The number of molecules which enter from the solid state, that is from the ice state to the water state, is equal to the number of molecules which go back from the liquid state to the solid ice. Therefore, at equilibrium, what do we observe? That the mass of ice and the mass of water, they are both constant. It appears as if nothing is happening. The mass of ice and the mass of water, they become constant. And we say, now they are, both ice and water are in equilibrium with each other. Why do we say they are in equilibrium with each other? Have you ever noticed that if you touch ice, your hand gets stuck to it? It sticks to it. Sometimes ice even sticks to your tongue or to your lips. If you take a cube and you're playing with it, it happens, it sticks. So imagine what happens when the water molecules which are in contact with the ice come in contact with it. They also stick to it or adhere to it. And when that happens, the molecules, the number of molecules that stick to the ice and turn into ice, that is solid, because now they can't move, and that's the difference. They are all H2O molecules, but the only difference between ice and water is that in water the molecules are free to move about, but in ice they are stuck at one place. So the moment the molecules, they get stuck to ice, at the same time a same number of molecules are escaping into the liquid, and therefore the masses of both water and ice, they become constant. So this is a state which is a dynamic state. It's not a static. It appears static, while actually it's a dynamic state because the rates of two processes, two opposing processes, is equal. Both the processes, that is melting of ice and freezing of water, are taking place simultaneously. They are opposite processes and they are occurring simultaneously, and at equilibrium they are not only occurring simultaneously, they are also occurring at the same rate. They are happening at the same rate, and that is when we feel nothing is happening. That is when we feel that it is a static state, while actually there is maximum action taking place at that time. So let's just read out the notes that I wrote for you. At 273 Kelvin, 1 atmospheric pressure, which is equal to 1.013 bar, if you take ice and water in a flask, it establishes an equilibrium, and the masses of both the substances, that is ice and water, are fixed. It's a dynamic state. Water, which is liquid, it adheres to ice on the boundary of the ice cubes. And ice and water, at the same time, the ice is melting and entering the water. Ice and water are at equilibrium. Now, this is important. At a particular temperature and pressure. If you noticed, We took ice at 273 Kelvin, that is 0 degrees Celsius, and water at 0 degrees Celsius. And the pressure was 1 atmosphere. This was a particular temperature and pressure at which this equilibrium could be established. If the temperature, let us say, was more than 273 Kelvin, if it was more than 273 Kelvin, then the ice would have melted slowly into water. If the temperature was less than 0 degrees Celsius, then the water would slowly have turned into ice. And the equilibrium would not have been established. So equilibrium between the two phases would be established at a certain temperature, and it would be established at a certain temperature at a certain pressure. And if we fix the pressure to be 1 atmosphere, then the temperature at which this equilibrium establishes between the two states, that is the solid and the liquid state, is known as the melting point of that substance or the freezing point of that substance. You know, the melting point and freezing point of water are the same. The melting point of ice is 0 degrees Celsius and the freezing point of water is also 0 degrees Celsius or 273 Kelvin. So if the pressure is 1 atmosphere for any substance, that temperature at which the solid and the liquid state will be in equilibrium with each other would be known as its melting point or its freezing point. So we'll say for any substance at 1 atmosphere, the condition is that the pressure should be 1 atmosphere, then the temperature at which they establish an equilibrium would be its melting point. The temperature at which the solid and the liquid are in equilibrium is known as the normal boiling or normal melting or freezing point. Again, at equilibrium, both opposing processes are occurring simultaneously, that is melting and freezing. Both the processes are occurring simultaneously, and not only are they occurring simultaneously, they are also occurring at the same rate. So this was about solid-liquid equilibrium, how it is established and how you define the normal melting and boiling point. The normal conditions are that the pressure should be 1 atmosphere or 1 bar. 1 atmosphere, which is 1.013 bar, which is approximately the same. So after having done this, let us now move to the next phase transformation. That is, we are now talking of liquid vapor equilibrium. A liquid is turning into its vapor. This time, what do? As I explained in part 1 to you, that we take water in a petri dish or in a china dish, whatever, in a jar. And in the jar we have an opening and we have connected a manometer to the opening. Now what is a manometer? A manometer is a glass tube which is in the shape of a U. It's a U tube made up of glass, and you attach it to one of the openings in the box there. And this manometer, in the U tube we fill up mercury, and you know mercury is a liquid metal. So when you fill up mercury in the 2 arms of the U tube, what do you see? That what is working on the U tube from here at this place on the U tube, you find that atmosphere is pushing the mercury downwards, and inside the jar also you have air which also has 1 atmospheric pressure. Therefore that also pushes the mercury down here. So the pressure on both the sides, in both the limbs of the U tube, is equal initially. Why? Because you have the atmospheric pressure pushing down the mercury in both the arms of the U tube. As a result of it, what happens? The U tube, it shows the same level of mercury in both the arms. Mercury in both the arms is at the same level. It means the pressure is the same. The pressure outside the jar and pressure inside the jar is equal. That is what we started with. Now, when we add water to this jar in a small dish, we just open the lid, we add the water in a petri dish, and we close the jar again quickly. So now what do we observe after a little while? We observe that the manometer starts showing us a reading. It starts showing the pressure inside the jar starts increasing. And when it starts increasing, it starts pushing the mercury down in this limb. Because now the pressure that the jar is putting here, it is more than the pressure which is coming down here. The atmospheric pressure is less. and the pressure inside the jar starts increasing, as a result of which the mercury in the manometer is pushed down, and we see a difference in the heights of mercury in the two limbs. Now mercury goes down in the limb, which shows that there is some pressure which is developing inside the jar. What is causing this pressure? We started with water, and water, we know, at all temperatures on the surface it evaporates. So water evaporates, and as water evaporates, what happens? It is again a process which is reversible. So if it's a reversible process, the water, it starts evaporating. Initially we started only with water and assuming there was no water vapor in the jar. And when the water vapor started rising, the manometer started showing, the level of mercury started going down in the limb here. And obviously that entire column was pushed up on the other side, and therefore the level of mercury rises in the other limb. Now as the amount of vapors keeps on increasing, the mercury keeps getting pushed down, and initially this is very fast. But after some time we notice that the speed with which the mercury was being pushed down, it decreases. The rate at which it was pushing down the mercury, it decreases. Why? Because as vapors are formed, these vapors, they also start getting attracted to the water. They also, some of these water vapor molecules, they lose their energy when they hit each other and they collide with the jar. Some of the molecules lose energy and they go back and enter the water, the liquid again. And therefore, they are no longer participating, they are no longer contributing to the pressure of the gas or pressure of the water vapor inside. So we find that after some time the opposite process also starts, and as the concentration of water vapor increases in the jar, the speed for the opposite reaction, the reactant is water in the gaseous form, that is water vapor. So as water vapor increases, the rate at which water vapor joins back the liquid also increases. And therefore, initially we felt that the pressure was going on increasing. But after some time we see the speed of the increase of pressure decreases, and then a point comes where now the manometer reading becomes static. It no longer is increasing, it has stopped. At this point, for this temperature, we say this is the vapor pressure of this liquid. It is the vapor pressure of this substance at this temperature. This is the vapor pressure of this liquid. So we say, let me just read the notes now. Water, liquid and gas are in equilibrium with each other in this. Both rates are obviously equal when equilibrium is established. That is why the manometer did not show any change in reading after the equilibrium was established. The rate of evaporation is constant. Initially, the rate of evaporation is constant. But the rate of increase of pressure decreases after some time. Why? Because rate of condensation starts increasing. That I explained, that the raw material for the opposite reaction is increasing, and as that increases, the rate of the opposite reaction increases. Therefore, it appears that the manometer initially was showing a very quick decrease in the level, but then it becomes slower and slower because the opposite process starts, and finally it comes to a stop at equilibrium. So, but rate of evaporation is constant, but rate of increase of pressure decreases because the condensation is also occurring. This vapor pressure at equilibrium is known as the equilibrium vapor pressure. And equilibrium vapor pressure is the vapor pressure at equilibrium which increases with increasing temperature. If I took the same water at a higher temperature, then the vapor pressure at a higher temperature would have been higher. And at a lower temperature, the vapor pressure, obviously, because at higher temperatures, the molecules would have more energy and more molecules would escape in the form of a gas. Therefore, the vapor pressure of a substance depends on the temperature at which you are calculating the vapor pressure. Different liquids have different vapor pressures at the same temperature. If I take different liquids at the same temperature and I check out their vapor pressures, they will have different vapor pressures. But what decides, which property depends on this vapor pressure? So the substance which has the highest vapor pressure, it means its molecules are most easily escaping in the form of a gas. They are the ones which would have the lowest boiling point. And they are the liquids that we say are very volatile. What is this property of a substance, of a liquid easily evaporating, known as its volatility? So a substance, that the one which has the highest vapor pressure, would have the highest volatility. Or we can say that it is the most volatile. And any liquid that vaporizes very easily at a certain, if you have three liquids and the one that vaporizes very easily at that temperature, you would know that since this vaporizes easily, its boiling point should be the lowest. And that is what is observed. That if you take methyl alcohol, acetone and ether, you notice that out of these, ether is the one that has the highest vapor pressure. And since it has the highest vapor pressure, the melting points are listed here. Methyl alcohol has a melting point of 64.7 degrees Celsius, acetone is 56.3 degrees Celsius, while ether is 34.6 degrees Celsius, which means the one that is most volatile would have the lowest boiling point. So we will now relate the boiling point and understand boiling point better in terms of equilibrium, just as we understood it in terms of the freezing and melting. What was the condition here? That the pressure was 1 atmosphere. If you lay the same conditions here, you get, instead of the freezing or the melting point, you get the boiling point. If you keep the pressure to be 1 atmosphere or 1.013 bar, at that pressure, the temperature at which a liquid establishes an equilibrium with its vapor state, or its equilibrium vapor pressure, it establishes an equilibrium with its vapor state, that temperature would be known as its boiling point. We'll understand that further. I'll just wipe this off and fill up the board again for you. Give me a minute. Okay, moving ahead now. Let us assume that we take 1 milliliter of 3 liquids, that is acetone, ethyl alcohol and water. 1 milliliter each in 3 watch glasses. And this time, we do not keep them in a closed jar. From our experience, we know that if we leave a liquid just open to the atmosphere, it eventually evaporates. The liquid, all of it evaporates and it dries up. How long that would take depends on a few factors, but all liquids at any temperature, if you just leave them out in the open in the atmosphere, no, I shouldn't say at any temperature, usually temperatures which are above their freezing point, if you leave them out in the open, they do evaporate. So if we take 1 milliliter of acetone, ethyl alcohol and water in watch glasses and we repeat with different volumes of the liquids, let us say that first we took 1 milliliter of each, then we start changing the volumes. In each case, we always find that eventually the liquid, whatever the liquid is going to evaporate. And how long does that take depends on the nature of the liquid, which means that how volatile is the liquid. A liquid that is more volatile evaporates more easily, and therefore that is the one that will evaporate first. The amount of the liquid, if you take a drop of a liquid, that evaporates faster, but if you have, let us say, 10 liters of the same thing, that will take much longer. So it depends on how much of work has to be done, how much of it has to really evaporate, and the temperature of the liquid. You know, how does temperature affect evaporation? Have you seen clothes dry up faster during summer days and they dry up slower during winter days? Well, how is the temperature affecting the evaporation? If there is more temperature, more molecules would have higher energy, and therefore more molecules would be able to escape the surface of the liquid in the form of vapors or in the form of gas. Therefore, evaporation would depend on these 3 factors. But if evaporation is occurring in an open vessel, can equilibrium be established? When we talked of the liquid and vapor equilibrium, I told you that when vapors are formed, some of the molecules of the vapors, they lose energy and they fall back into the liquid. And when does that happen? When they collide with each other, when they collide with the walls of the container. But here they are going out in the open into a much larger area, and therefore their collisions, there are no walls because they're going out into the atmosphere. So the chances of condensation are not there. Therefore, whenever you have liquids in open vessels, they cannot establish equilibrium. The reason being that although evaporation is taking place, condensation, at least even if it is taking place, it is not measurable, it's not visible, it's not possible. Because usually condensation does not occur. The vapors are simply lost into the atmosphere. So equilibrium cannot be reached in an open system as condensation does not occur in an open system. So water and water vapor, they can establish an equilibrium with each other. If the pressure is kept at 1 atmosphere, then they establish an equilibrium with each other at a fixed temperature. And that temperature is 100 degrees Celsius or 373 Kelvin. This 100 degrees Celsius temperature, from our knowledge, we know is the boiling point of water. So you can define boiling point in terms of equilibrium also. So water and water vapor are in equilibrium with each other at 1 atmosphere and 100 degrees Celsius in a closed. The condition is that the vessel should be closed because equilibrium cannot be established in an open vessel. I just explained it to you. And this temperature is known as its boiling point. So for any pure liquid at 1 atmosphere, which is equal to 1.013 bar pressure, the temperature at which the liquid establishes an equilibrium with its vapor would be known as its normal boiling point, just as we talked of the normal freezing point or the normal melting point. Now here, there's one thing that I would like you to think about. We talk of evaporation and we talk of boiling. What's the difference? Evaporation occurs at all temperatures. Just a cursory view about it. Evaporation, your clothes dry up at any temperature. But when they are wet, you leave them out to hang on the clothesline and they dry up. But when do you say that water is boiling? When your mom is making tea, that's when the water starts boiling. What's the difference between boiling and evaporation? Now I just made this. If you really look at it, if you have a liquid at any temperature like water, the molecules on the surface of the liquid, when they gain energy and they escape from the liquid, that process is called evaporation. What is happening here? The atmospheric pressure is pushing the liquid downwards and that makes a surface, it is like a wall. But some molecules, they gain energy and they escape from the top. Those molecules which are on the surface, that one layer of molecules, they gain energy and they just escape into the atmosphere and the process is called evaporation. But at 100 degrees Celsius, what happens? 1 atmospheric pressure is pushing the liquid downwards. But at 100 degrees Celsius, the entire water starts pushing. When the molecules gain energy, they start pushing the atmosphere upwards. And at 100 degrees Celsius, the pressure with which the atmosphere is pushing the liquid downwards becomes equal to the pressure with which the liquid is pushing back on the atmosphere. Therefore, at this point, the surface seems to vanish. And what do you see? All of a sudden, bubbles of water, that is gas, water that turns into water vapor. At that temperature, it starts coming even from the bottom of the jar. It starts coming out in the form of bubbles, and the surface seems to have vanished. It's all bubbly, and that is when we say that boiling is occurring. And that is the temperature when the pressure is 1 atmospheric pressure. At that point, when the pressure of the liquid becomes equal and therefore the liquids can escape even from the bottom, is known as the boiling. So, boiling point, in other words, what would it depend on? It would depend on the atmospheric pressure. I said that what is boiling point? We defined normal boiling point as that temperature at which a liquid establishes equilibrium with its vapor at 1 atmospheric pressure. So, boiling point depends on the pressure. But we know know that on mountains, the atmospheric pressure is lower. And if the atmospheric pressure is lower, the pressure with which the liquid water is being pushed down is lesser. Then at a lower temperature, the molecules of the liquid will be able to push it upwards, or the pressure would become equal on both sides at a lower temperature. And that is the reason why that at higher altitudes we find, or when you go up on mountains, we find that the boiling point of a substance is lesser on a mountain. Why? Because the atmospheric pressure is lesser. So we say here that for any pure liquid at 1 atmosphere, 1 bar, the temperature at which the liquid and vapor are in equilibrium is called its normal boiling point of that liquid, and it depends on the atmospheric pressure. And atmospheric pressure changes according to altitude. Therefore, the boiling point would also indirectly depend on the altitude where you are measuring it. So at higher altitudes, the atmospheric pressure is lower, and therefore the boiling point is also lower. With this, we finish the liquid and vapor equilibrium. And now we are going to head towards the third equilibrium, that is the equilibrium between the solid and the vapor phase, or the gaseous phase. Give me a minute to prepare the board again. Let us now talk of the next type of phase transformation, that is a solid vapor equilibrium. The process of a solid directly getting turned into a gas is known as sublimation. The process is known as sublimation. And let us just understand, there are few substances which can directly pass from the solid state to the gaseous state. For example, iodine. Iodine crystals are small crystals and they are purple in color, and they tend to vaporize on their own. If you keep them in a jar, in a closed jar, you find that the purple color, the iodine crystals which were at the bottom, after some time you observe the entire jar, it becomes purple. It has vapors of iodine. Especially if you warm it up, that is when the temperature, at a little higher temperature, the iodine vaporizes and it establishes an equilibrium at that temperature. And the intensity of the purple color, it goes on increasing until at one point it becomes stable. And that purple color becomes stable at that temperature. When that becomes stable, we say an equilibrium has been established between the solid state and the vapor state of a substance that sublimes. There are other examples of substances which sublime as well. For example, camphor. You know, your mom uses camphor when she is praying. It's usually used in prayers. And we talked of camphorated oil. So camphor is again a substance which is commonly used in households and which sublimes. Your mom uses naphthalene balls when she packs away the winter clothing, and the naphthalene, when you take it out in the summer again, in the next winter, you find the naphthalene balls have either grown very small or they've simply vanished. That's also because naphthalene also vaporizes, it sublimes. And since it sublimes, if you keep naphthalene in a closed vessel, it would also establish an equilibrium with the vapor. And ammonium chloride is another such example, which from the solid state directly vaporizes to ammonium chloride vapors. So all such substances which sublime, they can establish an equilibrium at 1 atmospheric pressure. At a certain temperature, they can establish an equilibrium between the gaseous and the solid state. So this was about the solid vapor equilibrium. With that, I will end today's video. If you found it helpful, please give it a thumbs up. Subscribe to my channel, recommend it to your friends, and please keep returning for watching more videos of chemistry. Thank you for watching, and bye-bye for now.